Okay, we'll get started. So welcome to ECE 5500. This is a course on nonlinear and dynamic programming. So first half of the course is about nonlinear programming. The second half of the course would be about dynamic programming. So we'll start dynamic programming around end of October, early November. How many of you have heard of the term optimization before? How many have been a user of optimization? No? Not a user of optimization yet, a few people? Okay, perfect. So you're in the right class. I'll be your instructor. My name is Abhishek Gupta. I've been a faculty in the ECE department for the last 10 years. You have my email ID in the course information sheet. The prerequisites for this class is 3050, that's signals and systems, or 5551. Or a grad standing in engineering, math, and physical sciences. But truly speaking, the real prerequisite is not any of these, but mathematical maturity, understanding of linear algebra, and being able to write code in either MATLAB or Python. Preferably Python, because Python is now the programming language for many different fields. But certainly if many of you are working in automotive sector or some of these different areas where MATLAB is more prevalent, you can definitely submit your assignments by coding in MATLAB. I'm comfortable and familiar with both these programming languages, so it's more important for me to be able to grade. So MATLAB and Python, both of them works. If you write it in some other language like C++, there's no way I'm going to be able to grade your assignments. But if that's what your preferred programming language is, feel free to reach out to me and we'll figure something out. This class has been running for many years, maybe like 20, 30 plus years at OSU. It ran previously as ECE 5759, and now the number has been changed to 5500. There are other courses like 6500 and 6501, which sort of builds upon the contents of this particular class. So if you're interested in the optimization track, feel free to, you're of course enrolled in 5500, but then you can take 6500 and 6501 whenever they are offered in the spring semester and try to understand like optimization holistically. The previous year's lectures of this class has been recorded, and as you can see, we are recording the lectures of this particular class as well. Generally, these recordings will be posted on YouTube, and so that you have access to these recordings even after you retire. And if you wanted to pass your time, you can go back to your optimization lectures. Also, some people are working, some people have other commitments, family commitments and whatnot. So it's very helpful for them to be able to access those lectures offline. And so that's why I've been recording lectures since 2018, and all my lectures are on YouTube. Office hours are going to be Wednesday 11 to 12, so right before the class starts. But if that particular time doesn't work for you, or if you want to meet me over Zoom, feel free to look up my calendar. My calendar link is on Carmen. So I'll be using Carmen for posting all the assignments and everything. So look up my calendar, figure out an empty slot, and then send me an email for that particular slot, and I'll be happy to meet you. The course text is going to be nonlinear programming, which is this book. Even if you have an older edition, that's fine, because the math hasn't changed in the last 100 or so years. So older books also work in today's world. The only thing is it doesn't contain dynamic programming. So the dynamic programming part is something that I'm going to collect from multiple sources, and we'll be covering that in the lecture. The evaluation policy comprises 6 homework, 3 online time quizzes. Those quizzes are on Carmen, 2 in-class midterms, and then 1 project. The 6 homework, so homework 1 has already been uploaded. So typically a homework should take you about 2.5 hours to finish. But if it's taking you more time, you probably are overthinking. So don't overthink. The homeworks are supposed to be simple and straightforward. But the homeworks are supposed to build your mathematical muscle in your brains. So some part of the homework is coding, but some part of it will be also understanding linear algebra, understanding optimization, and then deriving some equations, deriving some proof, in your assignment. So make sure so that at the end of this course, which is at the end of 5500, you're able to argue yourself mathematically, you're able to understand optimization very well, and you're prepared for taking other higher level advanced courses in optimization or do your research. I assume that many of you would be PhD student, but I could be wrong. Even if you're a master student and you are going out to industry after you graduate, a lot of industries are now using optimization in their day-to-day tasks. So no matter what industry you go to, the contents of this course will be very useful even in that particular industry. Now, that's the reason why I have a project and not a final exam, because what I want you to do in your project is pick up an optimization problem that might be beneficial to the industry that you are targeting. So if you want to go to Amazon and work for Amazon, you need to pick up a topic of interest that would be of interest to Amazon. Do some research on it, implement some piece of code, read some papers, create a project report which you will then submit it on Carmen, so that you can write about it in your resume, and then when you're applying to Amazon, they'll look at your application favorably because you have understood their domain very well through this course project. So that's the purpose of having a course project and not a final exam in this class. So think of course project definitely as a way to build your competence in a very specific area where you would like to look for jobs in the future. You have to write your own homework. You can definitely work in a group. You can take help from your peers. You can take help from me. But you have to write your own assignment. You have to write your own code. You have to submit your own PDF on Carmen. Or if you want to submit it in class, definitely feel free to submit it in class as well. The first midterm is scheduled on October 8th. We'll cover whatever, on October 8th, we'll cover probably assignment 1, 2, 3 will be finished by that time. So we'll be covering the assignment 1 to 3 topics in that particular midterm. Second midterm is on November 12th. We'll cover all the topics that we have covered until midterm 2. That will be part of the syllabus of midterm 2. There are no final exams here. There is a project report that will be due on December 8th. So whatever project you have picked, you have to write a 5-ish page report. There was a time when somebody submitted a 40-page report. I don't want to see a 40-page report. Just submit a 5-page report. Be reasonable, both on yourself as well as on me. Submit a 5+ page report, or submit your code. If you're writing a code, just submit that as part of your project report. Any questions so far? No?
How many homeworks?
6 homeworks. Yeah. It's given right here. Evaluation policy, 6 homeworks. Yeah. So the course has multiple objectives. So I would assume that many of you have a very weak exposure to optimization, but you have seen it somewhere. You might have used optimization algorithms in some project or the other in the past. So we really want to understand how do we model engineering problem as optimization problems. We learn the theory of nonlinear programming for both constrained as well as unconstrained optimization. So we'll start with unconstrained, then we'll move on to constrained optimization. We'll understand the algorithm. So it's very important to know, most of the people, when they think of optimization, they'll pick up a package in Python, they'll pick up a package in MATLAB, and they'll call that package in order to solve an optimization problem. But the goal of this lecture is to try and figure out, or this class is to try and figure out what exactly is happening when you're calling that package. Okay, so what's the algorithm running behind that package, which is helping you optimize the specific objective function and the specific constraints that you have. Okay, so this is an algorithms class. This is not a place where you will learn about different packages. What you will learn here is what's the underlying mathematics, what exactly is that package trying to do when it's being called to optimize a certain function. And then we'll also review convergence properties and computational complexity of some of the algorithms that we will be studying. So it's important that you understand that many of these topics are very mathematical in nature. We'll use linear algebra, we'll use what is known as real analysis techniques in this particular class. So when we talk about convergence, we have to understand sequences, we have to understand convergence of sequences, and so on. So I am going to cover all the prerequisites in the next 4 or 5 classes, which is we'll talk about norms, sequences, metrics, linear algebra, eigenvalues, eigenvectors, convex functions, convex sets, and so on. So we'll cover all of that, but it is implicit throughout this course that you have seen this somewhere, you might have forgotten about it, or you might not have seen some part of it, but you might have seen other part of it. So the goal for the next 4 or 5 lectures is just to build the basics upon which we'll build the rest of the course, but know that it is expected that you will know most of the stuff in the next 4 or 5 lectures. You would have known or seen most of the stuff before in some of the earlier courses or math courses that you might have taken. There is a list of topics that I have given, which will be covered in this class. For project topics, I have given a lot of different ideas. You can pick whatever project topic seems suitable to you. And then there is a bunch of statements and information that is given to you as required by the university. And feel free to go through it and let me know if you have any questions. Has everyone received the course information sheet? If not, okay. Assignment 1 is uploaded on Carmen, so you can take a look at it. But some of the thing will require, everyone has it? Okay. Some of the questions there would require us, I think, yeah, we'll probably have to have lecture 6. By lecture 6, we will be able to have all the stuff that is needed in order to solve the homework. So you can either start doing it now, or you can do it after, maybe perhaps towards the end of next week. Whatever you feel comfortable with. Okay. So let's get started. The first thing I want to talk about is vectors. Oh, any questions so far on the course evaluation? Midterm will be in class. So yeah, paper and pen. Any other question? So X is a vector in Rn. So all of you are familiar with this symbol in. So this is a set, this is an element of that set, and this is a symbol for in. So X is a vector in Rn. We will generally write X as x1, x2 to xn. So these are all the elements of the vector. We have a special vector called EI, which is like all zeros and 1 at the ith position. And consequently, you can write X as summation of xi ei, I equals 1 to n. So xi is a scalar, ei is a vector. This is a vector. I'm summing up all these vectors in order to get the vector x. We are just setting up some notations here. Now I have two vectors v1, v2 in Rn. They are called orthogonal. If and only if v1 transpose v2 equals to 0. Okay, how many of you have seen this term orthogonal before? I would expect everyone. Okay, good. Let's talk about norms. Well, okay, let me cover one specific result here. So if I have x, you have v1, vn are orthogonal, then x can be written as summation of alpha I vi. I goes from 1 to n. So I have a bunch of orthogonal vectors. Then I can write x as a summation of some scalars multiplied by these orthogonal vectors. So what that basically means is the orthogonal vectors would span the entire space Rn. Okay. You have a bunch of vectors x. I'm looking for notation. So I've used x, I've used v, I've used e. Let me use v again. So v1 to vn are linearly independent if and only if there does not exist a set of scalars alpha 1 to alpha n, not all zeros, such that alpha 1 v1 plus alpha 2 v2 alpha n vn is equal to 0. Linearly. So linear independence among a set of vectors is a very important property. And if we have a set of linearly independent vectors and you have a set of scalars alpha 1 to alpha n such that this equation holds, then it must be the case that alpha 1 to alpha n are all equal to 0. Let's look at an example. So my v1 is, so I'm looking at 2 dimensions, so I only need to have v1 and v2. So 1 minus 1 v2 equals to 5 minus 5. Are they linearly independent or are they linearly dependent? So the question there is, we need to find alpha 1 and alpha 2 such that they have to be non-zero, and if I can pick an alpha 1 and alpha 2 such that the sum of alpha 1 v1 and alpha 2 v2 is 0, then it means that they are linearly dependent. So what should I pick as alpha 1? Negative 5. Alpha 2, 1. Then I have alpha 1 v1 plus alpha 2 v2 equals to 0. These are non-zeros, so not all of them have to be zeros, not all zeros, but so these are non-zeros. Then this means that v1, v2 are linearly dependent. Okay. So if I can find non-zero alpha 1 and alpha 2 such that this equation holds, then they are linearly dependent. On the other hand, if I was not able to find, if all of them were identically 0, so alpha 1 has to be 0, alpha 2 has to be 0 in order for this equation to hold, then V1 and V2 are linearly independent. Okay, any questions so far? Perfect. Let's talk about norms. So I have a vector x in Rn. Then this is a mapping from Rn to R, or I should say 0 infinity, such that, so this is known as a norm. Norm of x is greater than equal to 0, and norm of x is equal to 0 if and only if x is equal to 0. So this is known as a positive definiteness condition. So norm of x is always non-negative, and if it is equal to 0, then it must be the case that the vector x itself is equal to 0. Norm of alpha x is equal to absolute value of alpha times the norm of x. And the third condition is the triangle inequality, which is given by this. Okay. So positive definiteness, this is if you multiply it by a scalar, so this alpha is in R. If you multiply the vector x by a scalar, you take the norm, you take the absolute value of scalar and the norm of x on the other side. So that's equal. And then the triangle inequality is that if you take a vector, you add it up, you take the norm, it must be less than equal to the norm of the sum of the norm of individual vectors. Okay, so this is a very important property, triangle inequality. And we'll use triangle inequality throughout this class, throughout this course, because it's a very important property and something that comes in handy when we are proving convergence of algorithms. Any questions so far? Okay. So what are the different norms that would be studied in this class or perhaps in your project? So we have L1 norm, which is denoted by norm with a subscript 1. This is summation I equals 1 to n xi. Then we have L2 norm, which is the usual Euclidean norm, summation I equals 1 to n xi square root. We have LP norm, this is the pth root, maybe I'll write it in another way. And then we have L infinity norm. This is also known as a Euclidean norm. And this is the norm that you might have seen in multiple courses you might have taken earlier, because L2 norm or Euclidean norm is the norm that is widely studied. A lot of people use it on a day-to-day basis. But in this particular class, we'll worry about other norms as well, as and when the situation arises. This is used heavily in dynamic optimization. If you were doing signal processing, L1 norm is used heavily. Optimization, L2 and LP norms come up frequently. I was once in a candidacy exam, and one of the problem that the student was trying to solve was movement of heart while the patient is in an MRI machine, and he wanted to get rid of a lot of noise that happens in those situations. And the reason why I remember this is it was really a very cool application of using a specific norm for solving that problem. And one of the things he spent significant time on was to figure out what is the norm that should be used in order to do denoising of that video signal, which is basically the video was coming out of an MRI machine which was capturing the movement of the heart. So it was a very interesting project. I was very excited to be part of his candidacy exam. Okay, so some people, especially those of you who are in PhD program and who might be doing signal processing or video processing or audio processing and so on, you will spend considerable amount of time thinking about the right norm for your specific problem. So it's an important topic. My research is focused mainly on dynamic optimization. So I'm generally not thinking about these norms, but I am thinking about this norm all the time. This is my bread and butter. Any questions so far? Okay. So every norm leads to what is known as a metric. Another important topic, as important as norm. So I have x and y. Both are vectors in Rn. I have a metric D. So depending on the situation, we'll sometimes use D, sometimes we'll use rho as a notation for metric. So this takes two vectors and then outputs something between 0 and infinity. And it satisfies exactly those, some of those conditions. So the first one is dxy is greater than equal to 0 and dxy equals to 0 if and only if x is equal to y. I think the second requirement is the triangle inequality dxy is less than equal to dxz plus dzy. Oh, and the third one is symmetry. dxy equals to dyx. And generally speaking, we'll be looking at the p norm of x and y, x minus y as a distance, as a metric between x and y. Let me show you a picture and that will make things clearer. I have a point x, I have a point y, this is my R n. How do we define the distance between x and y? Right? So the distance between x and y is basically a metric. What we are asking for is what's the d of x comma y looks like. Now, if we were looking at the L2 norm, the distance is the usual notion of distance. We draw a straight line between x and y, and we take a scale and measure the distance between these 2 points. That's our usual distance. But remember that we can pick any p norm. Okay, we don't have to stick to 2 norm. So what is L1 norm? So in L1 norm, you go from here to here, and then you go straight to y, and you take the scale, you measure this distance, and then you add up this distance, and that gives you the distance between x and y. So this is known as the Manhattan distance, or because if you look at Manhattan's map, it is basically a bunch of lines like this, and if you want to go from point A to point B, you have to go 10 blocks. I mean, suppose this is 10 blocks and this is 10 blocks. You want to go from x to y, you have to go 10 blocks down, and then you have to walk another 10 blocks in order to reach. There's no way to go from this directly to this. So that's where the L1 distance is useful. Okay. If you're looking at L infinity norm, so L infinity norm is maximum of this distance and this distance. Okay, so L infinity norm is a bit more abstract norm. We don't use it in our day-to-day activities, but certainly mathematically it's an important norm because you use it in dynamic optimization and whatnot. Okay, so that's L infinity norm. It's maximum of this distance and this distance. Any questions so far? Okay. Let's talk about sequences, if there are no questions. How many of you have seen norms and metrics in your previous class? A few? Okay. So I'm in a following setting. I have a collection of points. It's an infinite collection. So this is my x1, x2, x3, x4, something like this. Okay, so I'm getting a bunch of points. I've collected some points. So it's called a sequence. It's an infinite sequence, so k goes all the way from 1 to infinity. So remember this, each of these xk is a vector in Rn. So this is a sequence. What do you notice about the sequence? Okay, so I've created this sequence. What do you notice? Is there something cool that is happening here? So I look at x1 to x2, it's a very large distance, then x2 to x3 is smaller, x3 to x4 is further, even smaller. And as I see, as the sequence proceeds, it tends to do what is known as convergence. Okay, so the sequence is converging. When do we say that a sequence is converging? So xk, k equals to 1 converges to x bar if and only if. Now this is a mathematical definition of convergence. For every epsilon greater than 0, there exists an epsilon in the space of natural numbers such that norm of xk minus x bar, I'm using the norm, but let me use a metric. It doesn't matter what you use. Less than epsilon for every k greater than equal to n epsilon. We'll look at a few examples. How many of you have seen this definition or not? How many of you have not seen this definition of convergence before? A few people? Okay. So this is the rigorous mathematical definition of convergence. This is the definition that works in all dimensional spaces. Even if you are in infinite dimensional space, this still works. So that's why this definition is what everyone uses. So it's a convergent sequence if I can find for every epsilon greater than 0, I can find a natural number such that the tail of the sequence, so remember k is greater than equal to n epsilon. So the tail of the sequence is within epsilon distance to x bar. X bar is the point at which this is converging. Okay, so this might be x bar here. So this point here might be x bar. And if I look at the tail of the sequence, so I cut off the sequence at a specific point and I look at the rest of the sequence, it's within a epsilon neighborhood of x bar. So if I draw an epsilon ball around x bar, the entire tail of the sequence resides within this epsilon ball. And as I make my epsilon smaller and smaller, it doesn't matter how small this ball is, the tail, there is the tail of the sequence, and that tail lives within this epsilon ball around x bar. So let's look at a very specific example. My xk is 1 over k. This is a sequence in R. And my job is to find an x bar. Okay? So what does this sequence converge to? Any guesses? 0. Okay. It's still a guess yet because we haven't proved that this sequence converges to x bar. So right now our guess is 0 seems likely candidate for this sequence to converge. Now the only way I can prove that this converges is if I can find for every epsilon greater than 0, I have to find an n epsilon. So let's pick epsilon greater than 0 and let's define my n epsilon as ceiling of 1 over epsilon. So I pick the integer just above 1 over epsilon. So I picked epsilon greater than 0. I have come up with a definition for n epsilon. And let me pick k greater than equal to n epsilon. So what is xk minus x bar? It is 1 over k, which is less than equal to 1 over n epsilon, which is less than equal to epsilon. Actually, it's strictly less than epsilon. Maybe I'll have to add 1 here. So for a given epsilon greater than 0, I have been able to find a natural number n epsilon such that for every k greater than equal to n epsilon, what I have proved is xk minus x bar is less than epsilon. Okay, so now we have proved that this is indeed the point at which 1 over k converges. Any questions so far? Let's look at xk equals to k. This is also a sequence in R. Does this sequence converge? No? What is a likely x bar? Where does this reach as k goes to infinity? Infinity, right? So such a sequence is known as a divergent sequence. Okay, so it's not a convergent sequence, it's a divergent sequence because it diverges to infinity. Okay. Now let's look at another sequence. So this is not convergent, this is divergent. Let's look at xk equals to minus 1 raised to k. This is also a sequence in R. Does this sequence converge? Okay, so x1 is -1, x2 is 1, x3 is -1, x4 is 1. So the sequence looks something like this. This is my k, this is my xk. So I have -1, +1, -1, +1. This is what my sequence looks like. And so it's not convergent because if I pick an x bar, there is no x bar that I can pick such that this particular definition is going to hold. Okay? So consequently, this is not convergent. It's not a convergent sequence. It's not even a divergent sequence. The divergent sequence has to go to infinity, and a non-convergent sequence doesn't converge anywhere. Why do we care about convergence in optimization? What's so big deal? What's the big deal about convergence?
Algorithms need to converge.
Sorry?
Algorithms.
Yes. Yes. So whatever algorithm we design, it needs to converge. But what should it converge to? I have an optimization problem. I'm optimizing the energy cost of McDonald's, a McDonald's store. Okay? So that's the problem statement I have to optimize. So I go to my MATLAB or Python code and I punch in the numbers, I set up an optimization problem. And at the end of the optimization, it converges to something. What do we want that convergent solution to look like? It should be the optimal solution. It should be the point at which the energy consumption of McDonald's is optimized. Okay, so we want to set up an optimization algorithm. We want to come up with an algorithm that doesn't diverge and it doesn't come up with a sequence that is not convergent. We want it to come up with a convergent sequence, so it should satisfy this condition, and more importantly, we want it to converge to a point which is an optimal solution. Okay, we don't want it to converge to some random point in the space. Okay, so that's the reason why we care a lot about convergence. So throughout this course, whenever we come up with an algorithm, the first thing we'll care about is, does it converge? And the second thing we'll try to care about, we'll be caring about is whether it converges to an optimal solution or it doesn't converge to an optimal solution. Okay, so those are the two questions. So every algorithm, we'll study one algorithm in each class, and at the end of the algorithm, we'll try to understand whether it's converging, and if it is converging, does it converge to an optimal solution or not. Okay, any question? No? Awesome. So that sequence is, Cauchy sequence. Okay, so now I want to talk about Cauchy sequence. You know the problem with this particular definition? The problem is, if I am given a sequence, I have to be able to come up with this x bar, and then I have to check whether this condition is satisfied by that x bar or not. And if I come up with a wrong x bar, then I have to restart the entire guess. So let's say this xk, let's say our initial guess was, instead of 0, our initial guess was 1. And we couldn't come up with an n epsilon such that this condition holds. Then we have to go back and change the guess and do it. And then if it doesn't work, then we have to go back, change the guess, and do it all over again. So it becomes a problem. It becomes an iterative procedure to keep guessing and making sure that that particular condition is met. So here is something to our rescue where I don't need to know what the endpoint is going to look like. So xk, k equals 1 to infinity, is a Cauchy sequence. C is capital in Cauchy. If and only if for every epsilon greater than 0, there exists an n epsilon such that xk minus xm, oh, I have to use metric, for every k and m greater than equal to n epsilon. Yes.
Can you explain what the back? Can you explain some of the symbols of the music?
Yeah. Okay. So for every, this is for every. This is there exists. So for every epsilon greater than 0, there exists an n epsilon. This should be in the space of natural numbers such that the distance between xk and xm is less than epsilon for every k and m greater than equal to n epsilon. So both k and m has to be greater than equal to n epsilon. And if the distance is always less than epsilon, then it's a Cauchy sequence. And one of the major theorems in mathematics, actually the entire of mathematics, is in Rn, which is what we are studying here. Every Cauchy sequence converges. So Cauchy sequence is convergent. And actually the converse is also true. Any convergent sequence is a Cauchy sequence. That's only true for Rn, by the way. But that's one of the important theorems in mathematics. Every Cauchy sequence is a convergent sequence. Every convergent sequence is a Cauchy sequence in Rn. What's the cool thing about Cauchy sequence? It doesn't require knowing x bar. I don't have to worry about x bar. So for every epsilon greater than 0, I have to come up with n epsilon such that the distance between xk and xm has to be less than epsilon for every k and m greater than equal to n epsilon. So let's pick the same epsilon greater than 0, same n epsilon, and I pick k and m greater than equal to n epsilon. What is my xk minus xm? What is 1 over k minus 1 over m? Can you upper bound 1 over k minus 1 over m by something simple? Sorry? Yeah.
I was just going to say, since you're using the norm, the sum of the two for the
Sum of the two, okay.
triangle.
Yeah, okay. So sum of the two will definitely work, but I wanted. Okay, fine. We'll get to it. We'll have a little bit of a problem, but that's not.
Well, no, I meant just use a triangle. So
Yeah. So right. So you can definitely use triangle inequality, but this is less than 2 epsilon. Okay. So that's the problem. I mean, 2 epsilon is also okay. Like, it doesn't matter. We just rescale the epsilon, or we rescale n epsilon in order to get epsilon here. That's okay. But what I was thinking about is maximum of 1 over k and 1 over m. That also works. That's also a valid upper bound to 1 over k minus 1 over m. Okay, so I don't have to come up with x bar. I don't have to do any guessing game here. All I have to look at is 2 points in the tail, pick 2 points in the tail, look at the distance. If it is less than epsilon, then I'm good to go. I know that this sequence converges. Yes?
Where did 2 epsilon come from?
So 1 over k is less than epsilon and 1 over m is less than epsilon. Because both k and m are greater than n epsilon. So by the same reason here, it's less than 1 over n epsilon, which is less than epsilon. So that's where 2 epsilon comes from. Any other question? Okay. So whenever we are running an optimization algorithm, we are always looking for signals of a Cauchy sequence. Okay, and whenever we see that there is evidence that a sequence that the optimization algorithm is generating is a Cauchy sequence, we are done. We know that it's converging to something. We don't have to wait for the optimization algorithm to run for infinite amount of time, because nobody has infinite amount of time. So we don't need for it to run for infinite amount of time in order to prove that it is converging. So that allows us to come up with a stopping rule, what is known as a stopping rule for the optimization algorithm, that we see that there is an evidence of a Cauchy sequence. So we can stop and we can say that, look, we are now at an approximately optimal solution. And that's good enough for real world applications. Okay. So we talked about norms, metrics, sequences, Cauchy sequences. Next class, we are going to talk about lim-inf, lim-sup, subsequences, and then we'll talk about open and closed sets, and then we'll talk about matrices. Okay, so thank you so much for your attention. If you have any question, feel free to meet me right after the class, and I'll see you guys on Friday. Thank you.